Evening, everyone. So we're gonna try to solve homework number 3 individual problem. So let's read the problem together carefully. CityServe operates a small customer service center that receives incoming calls from customer. Each call is answered by one of several agents. So this is saying like we don't have only one agent. It's like there is one can also serve one customer at a time out of many other agents. Now, this is a scenario. This is not the given information. So it says if all five agents are busy, customers will wait in a queue. So meaning like if we have one customer, they're going to be served by one agent. We'll left for other four agents free. If we have like five customers, then at the time, all five agents will be busy. Now says that we have 20 can be waiting in the queue, meaning if we have, let's say, 23 customers, so three going to be served and sorry, 5 and 18 going to be in a queue and 5 will be served. Now, if we have a 26 customers, now the 26 customer going to be kicked from the system. And this is the information for the base model. So we have the enter arrival time of the customer. So we will receive like a call every 2 minutes. Like we have a call, then after 2 minutes from now, we're going to receive it another call. And if you look at that, if you want to do it through the queuing theory, so the rhetorical of this distribution going to be following a Boson distribution, whereas a half of customer going to be coming to the system every minute. Now the service will take up to 4 minutes with the exponential distribution. That's meaning like each time each agent handle a customer in average it will take him 4 minutes to be finished. Now, the base model asks you to do it through three agents. Okay. Now, we're going to do the analysis up to five for the cost analysis. And here is the cost associated for hiring one agent, which is $30. Waiting cost per customer is 10. And finally, the operational cost per customer is 25. Okay, so let's do that. So the first thing I want you to do is open a new FlexSim model. And we're going to use a source, a queue, a processor, and sync. Very simple model. And we're starting linking the objects in the system using a connector. Now we're going to start adding the information. So the source is following exponential. So by default, it is usually exponential with 2 minutes. Now the default setting in seconds. So you're going to change it into minutes. And now go to the processor. So the processor, we're going to go to the menu, statistical distribution, exponential. And this is going to be 4. And this is going to be in seconds, in minutes, sorry. Okay, so you can run this model to make sure like there is no faults. Yeah, I think the model is okay. It is very simple model, so no complaints. We can add this processor to automate this processor, make it more convenient. So we can just add this to group and call this group agent, where each processor represents an agent. And we can go to the toolbox and try to automate this to make it like more efficient. So we can add this one, added a parameter. So this is going to be integer. So this is going to be between 3 and 5. And our reference is the group of agent. So delete and copy agents. So this is a 3. We're going to go to this system. So this is going to be a 3. Now we can start collecting the statistics for this system. So let's do that. So first one is go to the queue, the statistics of the queue. We're gonna add the state time. So the state time, use the table because we want to look to the average, and this is for a queue. Now this system is kind of like become more complicated. So it's like there is different ways to handle the average time staying in the system. So just to have a peace of mind and relief, so we can go to the state time within the library of the dashboard and try to collect the when the system is creating the flow item until it is destroyed or terminated. So we can go with the composite state time with the table. And because like I want to just generate like 5 or 4 or different numbers of processors, so I don't want to have the hassle of that. So I can start from the source and collect it until it reaches the sink. Now we're gonna do also for the content. Okay, so for the content, we're gonna do it for the queue. And since we're gonna add these together, so this is like not an average, just adding these together. So it is okay, all right, to do it for all the processors. Okay, and we're gonna reset the model. Let's see if this is smart enough that it can capture for 4 or 5. So reset, yes. So you see, it's also already starting getting the information for 5. So let's go back to the 3 for our default model. Okay, since we have everything set up to run the model, okay, so let's start running the model. Now we're gonna reach out to the steady state system, so it is better to run it at its max. And after like a while, like let's leave it for a minute and so on. When you feel comfortable with the statistics, you can stop the model and just carry out the information. So it says here is in the average 107. So this is the average time in a queue, 107 seconds. For this guy is it, I guess, a 347. So 347 seconds. And for the length in the system, so the queue was 0.89, something like that. And for the others, so we can add them together. So 0.76 plus 0.67 plus 0.56, which is around 2. Okay, so this is the average. This is only in the processor. So we need to add it 0.9 there, which is the Q, or 0.89. So 2.89. This is how much length of the system. So we added all of these. Now let's go with a bonus question. Okay. So it is asked us to try to calculate the total cost if we hire 3, 4, and 5. Okay, let's open a Q model. Okay, I'm just curious if our number is matching. So in this case was 0.5, 0.25, and this is a 3 and 23. So this is going to be an hour multiplied by seconds. So this is in minutes. Okay, so you see the numbers are very close. They are very matching to what we have taken from uh, discrete event simulation. Now, let's say we're going to do the experiments to calculate the total cost. So this is the number of servers. And here we have a 3, 4, and 5 different potentials. And the question state we have 30 per server, 25 per customer waiting, and 10. Let's double check. Okay, so 30, 10, 25. So I have just switched these two numbers. Okay. Now let's calculate that. Like this is a good checkout point here, but I'm gonna relying on discrete event simulation numbers. So this is gonna be equals to 3, okay, by this value, 30, plus zero point 0.9 or 89 multiplied by 10 plus, this is like, this the length in a queue, which is was 0.89 plus 2 by 25, so 2 in the system. So it is 148, which is like almost the same number here. Let's go with this number. So 4 by 30 plus. Now we're gonna try to change this scenario here, and make it for 4 machines and run the simulation for infinity and see how these numbers are carried out. So this time is 0.17. Let's copy this table. It is saver to just move the statistics here. Okay, so this is equals plus 0.17 by 10 plus adding these numbers 0.7 plus 0.57 plus 0.43 plus 0.3 by 10 by 25, sorry. Okay, so it is 171. And now let's go back to the flex sim and change that to the 5 and reset the model and run it for a good period of time and copy and just paste the solutions here. So this is equals 5 by 30 plus 0.04 by 10 plus open parenthesis 0.67 plus 0.54 plus 0.39 plus 0.25 plus 0.14 by 25. Okay, which is 200. Let's try to see what the queuing theory give us. So you can see like almost the same numbers again. So 200, which is almost the same number. Of course, going to be slightly changes because of the physics, which is can be seen in the flex sim. Okay, so good luck.